Welcome to Unit 4 on Model Order Selection. I'm Sundeep Rangan at NYU. So model order selection really touches on one of the fundamental problems in machine learning, which is how after we train models, they generalize to new data that was not part of training. To illustrate this, I'm going to first walk through a very simple motivating example on polynomial regression. So just as a quick recap of polynomial regression, which we discussed in the previous unit, you have some data, x and y, and you have n samples of this. So if this is scalar data, it looks kind of like these blue dots here, with the x on the x-axis and the y on the y-axis. And what we want to do is fit some kind of polynomial relation between x and y. So just like we did in the last class, we can write that like this, where there are there's some polynomial order d, which will be called in this context the model order, and then we have some unknown coefficients. Now, if we knew the model order d, then we could solve for the coefficients exactly like we did in the previous unit using, say, least squares. You can check that out again from the end of the previous unit's section. The problem, though, is what do we do if we don't know d? And so somehow we have to learn this model order from the data. This is what is called the model order selection problem. Okay, to illustrate the simple polynomial model order selection problem, I've created again a very simple demo on the GitHub site. You can download the whole GitHub repository and run that demo on your local machine. But again, I'm going to go to the Colab research.google website like we did in the previous unit. After you navigate here, you can just click on the GitHub tab. Then you enter my GitHub site, github.com /sdrangan. Then we select the intro ML repository and scroll down to the demo in Unit 4 on polyfitting. After you press this, the Jupyter Notebook will open up. The first part in this Jupyter Notebook just opens up some basic packages. Sometimes it asks you to get permission to run the first command. These are the standard packages for NumPy and plotting and scalar. Now, for the data in this, I've created fully synthetic data. That means data that was created by this computer program, as opposed to actual measurements. And in this, what I did is I just took data x that was randomly generated from -1 to 1, and the true data y comes from some polynomial with some true coefficients beta. And what we're going to see in this demo is how well the learning can actually learn both the model order d as well as the coefficients. So to do this, we load a very useful package called NumPy polynomial, which has a whole bunch of routines for polynomial manipulations. We're going to just randomly select some true parameters and some noise variance. We generate the variables x, and then we generate the variables y from running through that true polynomial and adding some noise. So if you plot, let's run those commands. And then if we we plot the data, you get something like this. Now in reality, of course, the estimator will not know the true function, so it has to try to fit some kind of relation between x and y from this data. Before looking at fitting this, let's just plot what the true function, that is the true relation between y and x is. To do this, we scroll down here, and we generate a new set of points, x plot, a large number from -1 to 1, and we run this command here to plot or get the values for the true polynomial relation between x and y. Remember, beta are the true parameters in this model. And then we plot the true relation x and y on a red line along with our data points. When you run this command, you get this relation, this plot here, and you can see here that this is the true relation, that red line, and this is the data points deviating from that true relation because of some noise. So ideally what we want to do is look at these blue points here and somehow try to figure out or learn that red relation here. In this case, this red relation here is a third order polynomial. So first let's look at what happens if we somehow knew the model order, the true model order. So a genie tells you that, oh, the true relation between x and y is a third order polynomial, and you just have to find the coefficients. Now that problem we did in the previous unit, and you could use those tools. In particular, you can use the sklearn linear regression object. But since polynomial fitting itself is so common, we're going to use a specialized package. And actually that specialized routine is in this polynomial submodule in the NumPy that we loaded before. And to use it, it's super simple. So what we do in this case, we say, okay, fit a third order polynomial. So I'm going to say d, which is the model order, set it to 3, and just call this function polyfit with my data x and y and the model order, and then it gives me an estimate for those coefficients, beta hat. Now I'm going to plot the true function as I did before, and I'm also going to plot the estimated function on the same values here using the beta hat as opposed to the true values beta here. And just for completeness, I'll plot the data. So when you run this command, it fits it super fast. You get this graph here. So again, the red line is the true relation, and the green line is the one that's fit from the data. And you can see it's a very good fit. But this here was assuming that you had this genie that told you what the true model order is. Suppose you didn't know that. Well, maybe you're going to try different model orders. So let's look at first what happens if you try to fit a model order that's lower than the true value. Say, for example, that you try to fit d equals 1, which is just a linear relationship. We just set d equals to 1 and repeat the exact same code. So we get the coefficients for that first model order. We plot the true function, the estimated function, and the data. And lo and behold, you get this. Again, the red line is our true relation, and the green is our estimated value. Its green value is straight because we're just trying to fit a linear relationship. Obviously, we see here that the relationship is not very good because it can't capture the complexities in the relation between x and y. So this is what's called underfitting. Now let's look at an opposite problem. If you pick d to be too large, let's say, to make it a little extreme, I pick d is equal to 10. And let's run this code here. It's exact same. If we scroll down here, we'll see the graph. The red is the true relation, and this green relation is like this. What you see here is that the green relation is actually much more complex than the true relation. It's squiggling around like this. And that's because it's really trying to fit parts of the data that are just from the noise in this, not really the underlying relationship. And we'll discuss this more. We'll also see that once we go out of the region that the test data was on between -1 and 1, it starts to give crazy values because it deviates very fast. This part here, this kind of behavior is known as overfitting. Now, The question then, okay, so we can trial and error different values, say 1 or 10, and how would we try to pick the correct D between the range of possible Ds that we could have? Well, let me give you a very simple idea, which turns out to be a bad idea. What I'm going to do is just do a simple loop like this. I'm going to pick a number of values of D to test. And I just do that with this command here called dtest. So I'm going to pick numbers from 1 to 14. Remember that in Python, when you use this range command like this, this will end on 14, the number before this. And for each value, I'm going to fit a polynomial, just like I did. And I'm going to measure how close that fit is to the training data. The way I do that is I make a prediction of what the values would be in my model. And I look at, say, the mean squared error between the measured and observed values. And I stack them into a list, and I plot that value as a function of the model order. All right, let's just run that. It's very fast. And this is what we get. We see that for very low model orders, it fits very poorly because this is the RSS on the training data. And when I pick the correct model order, it suddenly drops down. But then as I increase the model order more, it continues to drop. Now this you might think is a little surprising because I'm not picking the correct model order anymore. But actually, if you think about it, you would realize that it's not actually unexpected that the model order, the mean squared error would continue to decrease. The reason is that the higher the model order, you're able to better and better fit the training data, even if that's actually not fitting the underlying relationship any better, but it's fitting that data better and better. As a result, this mean squared error, or RSS per sample, continues to go down. Now, one consequence of this is that if you look at this graph and you say, oh, I'm just going to pick the model order, which gives me the lowest RSS on the training data, you'll always pick the highest model order. So in this case, you would have picked 14. And in fact, if you went up higher and higher, say to 20, you would have picked 20 as well. So clearly, we need a better way to pick the model order instead of just looking at which model order gives the lowest mean squared error on the training data. Now, I want you to, before you go on to the next unit, try to think about some ideas yourself. And if you want some inspiration, I've left this very simple in-class exercise in the Jupyter notebook that you can try out. The basic idea is to generate some new data points and see what happens.